I think we are ready to start the next talk. The second speaker of this session is Teruyuki Yorioka from Shizuoka University, Japan. And the title of his talk is Preservation of Cohen layers. Go ahead, please.
Okay, so thank you very much for organizers for inviting me of this conference. At first, I will give a talk of the motivation of my topic. Can you hear me? Is it okay?
I think so.
Okay. Okay, I will start the Galvin's theorem. He showed that CH implies that for any family of graph subsets of omega 1, there exists of type R2. Oh, sorry. So RF too many also RF too many a family for any family of RF too many club subsets of omega 1, we can find uncountable subsets of F which can be diagonalized. And next, so Abraham Schiller proved that the Galvin cell in the Galvin theorem, CH is necessary in some strong sense. That is, it is consistent that there exists a family of many club subsets of omega 1 such that for any uncountable family of A, the intersection of for any uncountable family F prime of F, intersection of F prime is finite. So this shows that in the Galvin theorem, CH is necessary, and moreover, so remark. It cannot be diagonalized without collapsing R1.
Sorry, diagonalized means mod finite?
Mod bounded. Okay, so I will explain. So F prime is diagonalized. That is, thank you, Osvaldo. There is a club subset of omega 1 such that for any prime in F prime E minus, no, yeah, E minus E prime is bounded. Yeah. This means this means that diagonalize F prime. So, any comments or question? No? Is it okay? So, Abraham-Schiller theorem is a little involved, not so straightforward. So Justin Moore introduced introduced another family of Alpha many club subsets of omega 1 as follows. I explain such a things. To explain this, okay. Okay. So now let's see the radar system. And so now for a while, we consider 2 to the base on omega as a discrete space, like omega, and consider 2 to the base on omega. This is the product space of the discrete space. It's like we consider this product of space like a Baire space. So, okay. So now let R be real and X is a subset of our Baire space. And subset E of omega 1 is called sorry. Oh, I miss English. So a club subset E. So we define that a club subset of E of omega 1 captures are relative to C and X. But so C is fixed, so we omit C. If and only if for any limit point of delta in E, there exists a function f of x. Sorry, f and epsilon less than delta, such that for every c in intersection delta minus epsilon A of C delta intersection. The size of the C delta intersection C is a subset of R. So for each limit point of E, so we can find such a F and epsilon. So this calls that E captures R relative to X. Okay. I will mention the proposition. This is due to Justin. Okay, so now suppose that R is the subset of the control space, and X is a subset of our bare space, and each member of X is injective, and the size of X is R2. Moreover, for every R in R, we can find club ER which captures R relative to X. Moreover, I will write here. Moreover, a family of club sets ER is diagonalized. Then size of R have to be less than or equal to alpha. So this is the frame of the proposition. Okay. So I will give the proof of this one. This proof is not difficult. So suppose that suppose that the club subset E of omega 1 diagonalize ER, the family of ERs, and the size of R is greater than or equal to R2. So now we suppose that the size of R is R2. So now E is a club subset of omega 1, and E diagonalize each ER. So by counting the argument, then we can find eta such that the set of R prime, which is a set of R in R such that minus R is a subset of eta E of size R2. Okay. And now, oh, sorry. Yeah, I missed here. No. X, the size of X is not R2. No, now the size of X is R1. This is very important point. Sorry. So the size of X is R1. So, and R prime is so each captures R relative to X. So we have so now take delta in minus eta, which is limit point of minus eta, and then we have F in X and epsilon less than eta, such that set of R prime, R prime, which consists of the R in R prime, that for every C in intersection delta minus epsilon, the F of the size of C delta intersection C is a subset of what captures R. Size RF2. No, sorry. Here should be ER. However, this is a contradiction because you see, so for each R in R prime, above eta is a subset of ER. And delta is the limit point of E minus E above eta. Therefore, for every R in R double prime, for every C in E intersection delta minus epsilon, this set is a subset of R. But such a R have to be just one, at most one. But that R, the size of R double prime is of size R2, at least two different reals. This is a contradiction. So this proportion has been proved. Okay. So by from this proportion, Justin introduced can I erase the proof? Is it okay? So I want to mention the okay, so definition. So this is due to Justin. So claims the assumption C is defined as follows. Yeah. Is the X, which is a subset, which is a subset of our bare space of size alpha. Then this R, which is a subset of contour space of size alpha. Oh, sorry, which is of size alpha2. And for each R in R, there exists a class subset of ER, which captures R relative to X. Yeah. This is assertion C. So then, remark that in the assertion C, the family of club sets can be diagonalized without collapsing R2. Sorry, I forgot. Each, but this is not so important here. Each member of X is injected. Okay, so yeah, Moore proved that it is consistent that assertion C is consistent. If GFC is consistent, so C is consistent with GFC from the consistency of GFC. So the proof of this theorem is much easier than this one, because we can force C by a countable support iteration or proper forcing. Idea over proof. Up proof. So given X and R, so X is fixed. At first, X is fixed in the ground model, and R is in the contour space. So let X be the forcing notion. Which consists of all the is a segment of graph subset of omega 1 we want with their limit point. So you know, so P is a forcing notion, which are the club subset ER, which captures R relative to X. So point is that if omega then PXR is proper and as no yes and Alf's PIC. If X is on omega, we can show that this PXR is proper. And so and PXR has no new reals. However, I think so. This is very similar. This forcing is very similar to the forcing of MRP. So this may not. I guess this is not sigma cross. However, this is omega. How to say? This has no new reals. And under CH, this forcing notion is Alex PIC. So the countable support iteration of PXR of length less than or equal to omega 2 preserves omega 2. And this is proper. So this countable support iteration of PXR preserves omega 1. Therefore, the countable support iteration of forcing notion of this form with some suitable bookkeeping argument forces the assertion. This is very easier than the proof of Abraham Shirer's one. Okay, so okay, so remark. I define Q X R for such X R and R with models as type conditions to ER, which is a club subset of omega 1 and captures R relative to X. But this QR is a finite forcing notion forcing notion by finite approximations. So this QXR as new real. This is quite different from the Justin's PXR. So we need to take care of this this point. Oh, yeah. So point is that if X is non-meager, then QXR is proper and R2TIC under CH. Moreover, almost preserves square subset Cohen. In the sense of Martin Goldstein. So which means that roughly speaking, this forcing notion preserves Cohen layers. And this almost preservation of square subset Cohen is closed under countable support iteration. So countable support iteration of forcing notion of this form with some suitable bookkeeping argument forces the assertion C. So this is a different proof of the Justin's theorem. Why I introduce the finite forcing notion with models outside the conditions? So this is because that I want to force the assertion C by Aspromotor iteration. So this is the joint work is Tadatoshi Miyamoto and Justin Moore, and this paper has not been completed yet. So I will call here project. So I define motor iteration P kappa, where kappa is a regular cardinal greater than or equal to omega 2. And this P kappa has two following property. One is that P kappa forces C. Moreover, if kappa is larger than omega 2, then P omega 2 plus, oh, so no. Yeah, P omega 2 plus 1 is not proper. So yeah, this is our aspirator iteration is not a past, is not this aspirator iteration is a very little it has a little strong form. So this is not a this is different from aspirator iteration in their first paper. First paper is okay. So this aspirator iteration consists of this aspirator iteration uses a symmetric system with symmetric markers. So this is the point. Therefore, so we have this property. So now I proved it, and now Professor Miyamoto and Justin checked my proof. So my proof is not my proof has not been completed yet, I guess. But I think this is okay because Professor Miyamoto has a proof by himself. So two different persons prove this by different ways. So I think this is okay. So if this is okay, this is clear. This is trivially true. So the point to show this, there are a couple of points, but the basic but important point is that the collapse almost does clear subset Cohen. So the rest of my talk, I will explain the proof of this one in the rest of my talk. Any question or comment so far? I can't hear any voice from you.
Can I ask a question?
Yes, please.
So you want to force C together with continuum large or something like that?
No, of course I want, but it cannot. It cannot.
So
C implies that continuum is less than or equal to R3. I think so.
So C implies
that the continuum is less than or equal to R2. Continuum is have to be R2? I'm not sure. Yeah. Continuum have to be greater than or equal to R2. So C implies that continuum is R2. I think yeah, I think so. No? Oops. Yeah, no. Sorry. So I'm not sure. Yeah, you are right. Sorry. I completely missed.
So sorry. So you constructed P kappa poset.
Yeah. So yeah, I yes. So yeah. I claim that. My kappa forces C plus the continuum is equal to. Yeah, I think this is the important point. Yeah.
So I don't know if kappa is large, then P kappa collapses many cardinals.
Yes.
Oh,
I want to say.
I see. Thank you very much.
But No. So sorry. I missed very important point. If here have to be RT, P RT. Oh, I missed. Sorry. You are right. Sorry. Yeah. P omega 2. Here should be omega 2.
I see. Thank you. Okay, can I also ask something?
Yes, please.
So if C holds, then CH fails, right? That follows from Galvin's theorem or what? I mean, the continuum has to be at least Aleph 2, right?
Yeah.
So in this, what happens in Justin's original proofs? Because his forcing does not add reals, but then the iteration adds reals. Is this what is happening?
I'm not sure. Maybe Miyamoto Sensei knows much about this. This is very similar to the MRP situation. The situation is very similar to MRP. So MRP forcing is proper as non-new reals in Justin's paper.
Excuse me, this is Miyamoto speaking. CS iteration doesn't preserve sigma bareness. At the limit stage, sometimes you add new reals, even though iterans are sigma bare.
Sure, I know that. So
Okay.
that's what I'm asking. So this is an example of this, right? So we
Yes,
have an iteration where you add no reals, but in limit stages you add reals,
Yeah.
right?
Yeah.
Okay. And one more question.
Yes, please.
You preserve this this Cohen relation, right? Is this?
Yes.
Does this mean basically preserving non-meager sets, or?
Yeah. Yes.
Okay.
I think so. Square bracket preservation of square bracket Cohen is stronger than the preservation of non-meager sets.
Oh, okay, yeah, okay.
I will explain such a thing from now. And in the 15 minutes.
Okay, thank you.
Okay. The definition. Now red probably some regular cardinal. In somewhat large in your favorite context, and P consists of the finite division chains of countable elementary models of H kappa, and order relation is a superset relation. This is called Epsilon crux in a Stable's book. Okay, so we prove that the following claim. Suppose that theta is a large enough regular cardinal, and N is a countable elementary submodel of H theta with H kappa in N, and C is Cohen over N, and P is a member of P intersection N, then we can find P plus, which is the extension P, moreover, which is NP generic. Such that P plus forces that C is still Cohen over N0. That is P almost preserves square bracket Cohen. I want to mention some history. At first, Zapleter proved that P preserves additivity of measure zero ideal. Next, I proved that P has no random layers. That is, P preserves the covering number of measure zero ideal. This is the next step. This preserves the uniformity of the megasets. But I'm not sure, but I think that P has Cohen. So this is the end. Okay. So now given N and C and P, so P plus is have to be defined this one. So P is P union the N intersection H kappa. So we will show that. P plus forces this one. So now assume that dot is in N and F is at P name for nowhere dense subset of 2 to the omega, and Q is the extension of P such that Q forces that C is a member of F dot. Then I want to show that this is a contradiction. Okay. To show this, so we consider the following. For each initial segment new and each which is a member of H kappa, E new A is a set of a member of epsilon clubs such that R contains Q intersection N. And A is contained in all members of R minus Q intersection N. And R forces that C is a member of F dot. So then collection of E nu A. The member of N, because N has H kappa, and moreover, so define Y. Y is a set of the Y consists of the member X of control space such that for any K in omega, for any A in H kappa, E X restricted to K A is not empty. So then we claim that Y is nowhere dense. So yeah, at first I will check that Y is nowhere dense. To show this, let nu be 2 to the less than omega, and take Q prime, which is the extension of Q, and nu prime, which is the extension of nu, but the initial nu prime is in 2 to the less than omega, such that Q prime forces that the basic open interval by nu prime intersection F dot is empty. We can find such a Q prime and nu prime because F dot is a P name for nowhere dense subset of control space. So sorry, so I erase you. But then you see, yeah. So now let R be in the set epsilon nu. No, sorry. We want to show that. Want to show that nu prime intersection Y is empty. E X is a member of nu prime intersection Y. Then nu prime is the initial segment of X. So we can find R in E nu prime Q prime. But then Q, so R contains Q intersection N. Moreover, every member of R minus Q intersection N has Q prime. And Q prime is an extension of Q intersection N. Therefore, Q prime union R is a member of P. However, this is a contradiction because Q prime union R is an extension of Q prime. So Q prime union R forces this one. Oh, sorry. I missed here. Sorry. Yeah. Here should be that new intersection F missed here. Yeah. So you know, these are contradictions. Yeah, because x is the initial segment of new prime. Yeah, sorry. So R, so Q prime union R is the extension of R. So R forces the new prime intersection F dot is not empty. However, Q prime union R forces that the basic open interval by new prime intersection F dot is empty. So which is a contradiction. So now C is Cohen over N, and now Y is a member of N because Y defines the parameter of this, and this set is a member of N. So Y is a member of N, and C is a Cohen over N. So C is not a member of Y. Therefore, there is this K in omega, there is this A in H kappa, such that E of C is take to K A is empty. However, now since C is to K is a member of N, so we may assume that A is a member of N by elementarity of N. But this is a contradiction because our Q is a member of E of X K of A. Because Q, so our assumption is that Q poses that C dot is a member. No. C is a member of vector. So no. Sorry, here should be C. Yeah. So this is a contradiction. So our proof. So our claim has been proved. Okay, so that's all. Thank you very much.
Okay, thank you, Teruyuki, for your talk. And do you have any questions or comments?
Oh, okay. Can I ask something?
Yeah, please.
Go ahead.
Oh, so you mentioned you don't really know whether you add Cohen reals, right?
Yeah.
Do you know anything else about, I mean, what kind of reals you add, or not really?
I'm not
I mean,
sure.
I think it would be interesting to know to what extent this model is different from Justin's original model, because in Justin's model, the single step doesn't add real, so the Hull forcing will still have the sex property even though it adds real. So you have continuum large, but then all the cardinal invariants are small. So here you could ask, I mean, probably some cardinal invariants are large. I mean, this is just what I thought about.
Okay.
And the other question I have is about right. So what is I mean, you said this forcing is just works for Rlef2, and then if you make at Rlef2 at omega 2 plus 1, you already collapse cardinals, right?
Yeah.
But do you actually know that C implies that the continuum is Rlef2, or can it, or is this open?
I'm not sure. Maybe. I'm not sure. Maybe. How do you think about it? I'm not sure. Maybe. Miyamoto Sensei, do you have any comment about that? C implies the continuum should be able to?
Miyamoto speaking, we have no method to blow up the continuum larger than, greater than omega 2. CS, we are talking about either CS iteration or aspiromotor iteration.
Right, yeah. Well, CS iteration, of course, I know, but
right, but
aspiromotor,
because
sometimes there are methods to make the continuum larger, right?
Yeah, but in this case, we collapse omega 1.
Okay. Okay, thanks.
Yeah.
Right. Osvaldo, just go ahead with your question.
Well, no, just regarding the question of York, the question was about the side condition, about which kind of real seed adds. It was about the epsilon collapse or the other one?
For example, epsilon collapse. Do you know something else?
Well, the epsilon collapse is strongly proper. So it means that every real in the extension lives in a Cohen extension.
Yeah, you are right.
So in terms of reals, it's just Cohen. So the usual cardinal invariant will be the same as the Cohen model.
Oh, thank you very much. Yeah, you are right. Yes. So epsilon collapse as Cohen real.
Yes, that's Cohen reals. And only those. Every new real lives in a Cohen extension.
Yeah, you are right. Yes. Yeah. It's the
And is this still true? Is this true for the whole iteration, right?
Yes.
I see. So Cohen reals are really the only reals. I see. Okay. So this is very different from the countable support iteration. Okay. Thank you.
Yeah. Thanks, Osvaldo. Thank you very much.
Oh, thanks, Steve.
Right. Any other comments or questions?
I think this is Miyamoto speaking.
Yorioka-san,
you should mention there is a gap between stable poset and your purpose, because you want to force club subset of omega 1, but stable poset doesn't force. So there is a gap.
Yes. So how to say? So yeah, this collapse kappa to be omega 1.
Well, I mean, you are not adding club subset of omega 1 by stable poset.
No. So I want to say that this is the important. So this claim is a very important point. you see. Yeah. So QXR is Yeah, of course. So I would say ALP2PIC version of Epsilon clocks works well. So how to say? ALP2PIC version of Epsilon clocks preserves is proper, and ALP2PIC and CH, and almost preserves square subset Cohen by a similar argument, similar proof of our this claim. So I want to say that this is a very basic argument, but this is my first step, you know. So Miyamoto Sensei doesn't work my idea at first, but I proved it.
Miyamoto Sensei, is that okay?
Okay.
Right. Any other questions or comments? If not, let's thank the speaker again. パチパチパチ。
どうもありがとうございました。
And